All right, today's lesson is on fundamental forces. We begin with the bell ringer. If you're watching this video later, go ahead and pause. Try to do this bell ring on your own before you go over it, but they've already had time, so I'm going to go over it right now. So here we go. Pause. Here we go. Question number one. What is volume? Amount of space an object takes up. So what's the most voluminous thing in this room? Air. Air is correct. A lot of people will answer the room itself. We do not define negative space in science, meaning that the room is humanly defined, not by us. So if anything that takes up space, there has to, the amount of space an object takes up, there has to be an object for something to take up. Yes, air is the most voluminous thing in this room. Okay. What is mass? So the definition for mass is icky for a whole host of reasons. What did you say your definition was? 100% right. And that's a great chemistry answer, and it's a perfect chemistry answer. However, the issue with that is it's not helpful, because your average human being, if you guys are very smart, so you know that definition. But I think if your logic and question the definition for even a half a second, what's the first natural logical question that should come out of that? Nope. How are you not questioning it? Great, guys. If the question is the amount of matter an object takes up, what is the next question? What's matter then, guys? Okay, great. What's matter? Blah, blah, blah. Yeah, we got too much to do. I'm sorry, great job. Moving on. What's matter then? This doesn't seem helpful. This doesn't seem helpful for anybody involved. Okay, so amount of matter in an object, or the other definition a lot of times is anything that takes up space or anything that uses atoms. The problem with those last two definitions, those are also very common, is if you break those down in terms of English, there's a prepositional phrase, that takes up space, or that's made up of atoms. And that prepositional phrase describes the noun right before it, which is the true definition. Take out the prepositional phrase out of those definitions. What's mass, guys? Anything. Anything is the definition. That's unhelpful. We're going to give you a definition that we're going to use in here, which I will tell you right now for reasons in chemistry is wrong, okay? But it serves a very good purpose in here, and so that's why we're going to use it. That being said, we use Bohr's model all the time, and we technically know it's wrong too. Moving on, number two. What was kinematics for? We spent 2 months on it. It feels like you should answer this quicker. Many of you got good grades on the thing that we did the other day. Feels like you should answer this quicker. What was it for? I don't know, but I can do it real well. I got an A. I got an A! Who cares what it's for? What's it for? I'll give you that. Description of motion, or a little bit more basics, okay? If you want like really mechanically, give me 3 variables, I'll give you a 4th, okay? Probably one of my best ways of describing it is, give me some initial conditions, and I can describe the motion of an object, okay? The two main initial conditions that we usually look at is what's the initial velocity and what's the acceleration of an object, aka acceleration is how velocity changes, velocity initial is where it starts, and those are usually 2 of the 5 variables that you need, and that 3rd variable is usually the one that's asking the question after so much time, after it's gone this displacement, after blah, blah, blah. All right, what's the atom look like? I said specifically a carbon atom, but what do you got? What's the atom look like? You were in chemistry last year, okay? I always have students that complain about the chemistry teacher. By the way, there's certain subjects everyone complains about always, like every high school across the nation, my classes, throughout all of time. Chemistry is always one of them. Either you don't like the teacher or you do like the teacher, but everybody complains in some particular. Calculus is the other one. I don't know what. Anyway, it's not important. Point being, if you were alive and around the classroom through osmosis, you should be able to answer this question. What? No, I'm sorry. My apologies. Forget your chemistry class last year. You were in 8th grade. What's the atom look like? What's that? My gosh. What's in an atom, boys and girls? Okay, look, I know that's condescending, but this deserves it, all right? There's times where it's not okay to bully. This is an okay time, okay? Here's another one. He's just what? What? You know you deserve it. You know. You know why I know you know? Because you said what, but you had a smile on your face. All right. What's in an atom?
Protons.
Thank you. Where do the protons go?
In
the center. If it's a carbon atom, how many? Six. Thank you. 1, 2, 3, 4, 5, 6. Great. Where do the neutrons go? In the center. If it's carbon, the standard carbon is carbon 12. How many neutrons? 6. Although if it's an isotope, it could be 7 or 8. Look at me drawing Bohr's model, even though we know it's wrong. All right. How many electrons are on the outside? Assuming it's neutral, yes, although that can totally change. We'll go 2 in the first orbital, 4 in the second, like I'm actually attempting to do s, p, d, and f orbitals. I mean, come on. Electrons don't actually exist in a particular spot until you measure them, but we'll not get to that until Chem Physics 2. All right. Fundamental forces. This is what it looks like. That's all I need you to know right now. Let's move on. There are a lot of things today. I do love this conversation. Many forces chapters do not begin with this level of depth that we go into, and here's why. Spanauer fundamentally believes as a person, I don't know why I talked to myself in third person there, but I did, so I'm just going to stick by it, that short truths are kind of like lies. Meaning, you can give a small answer to a question and it can technically be correct, but it does not tell the whole story. I believe that very fundamentally about understanding forces as well. I could tell you why these things are what they are, and we'll zoom past this for some people who need us to a little bit later on, but for a lot of you that want to understand this at a depth of truth, we kind of need to begin at the beginning. What are fundamental forces? Well, based on this, fundamental forces, there are no forces that are not these. As we understand science stands today, there are 4. It is just 4 that we understand. That's it. Okay? Let's move on. So our answers real quick. I'm going to go through this real quick. Yes, volume is anything that the amount of mass an object takes up. Okay, so simple stuff here. Which has more volume, beach ball or bowling ball? Beach ball, because it takes up more space, right? Doesn't matter anything else. Okay, but mass, we're going to say, mass is the number of atoms an object has. As I mentioned earlier, that definition is technically wrong. Okay, you want to put a giant asterisk on that. Okay, I could talk about why it's wrong until I'm blue in the face, but the most important thing is your definitions that you gave me earlier for mass are more correct, but I would argue less helpful, because again, I said, what is mass? And you basically said, it's anything. Great, that's not helpful. So what is it? It's the amount of atoms an object has. If I could go to Kieser and count every single atom inside of him, it would be a very large number, and it would take me my entire life, and he wouldn't be able to move, so his life too, and be several lives over, actually. It's a very large number. Point being, if I knew that number, and I could tell you that number, and I could write that number on the board, that is the amount of mass that Kieser has. Sort of. All right, mass has 2 properties. This is going to be annoying for some of you, I apologize, but it has a first one and a second one. I'm not trying to be a butt here. This is a placeholder. This is where it needs to go, but I don't like to write down definitions until we talk about them. So for right now, write this down, write a 1 and a 2, put a box around it, and then later today, when I give you the first one, you can fill it in, and later this week, when I give you the second one, you can fill that one in. Also, quick point on notes. In many ways, I'm going to go too fast for some of these notes. These notes are already on Google Classroom. You could even pull them up now if I go a little bit too fast for some particular reason, or check them a little bit later. Also, I'm probably going to say more about these notes that should be written down than is up here. Okay, this is a placeholder. This is a structure for what should be there. But if you are only copying these things, you're not copying enough. And if you're not using your brain while thinking, well, it's not helpful at all, then is it? All right, mass is not weight. This is a very common assumption that a lot of people have. They are closely related. We're going to get into that relationship today, but they are not the same thing. Many scientists even use it incorrectly, mostly for the common person, to talk to the common person and just say, all right, I don't want to explain this whole thing to you right now. It works. Let's go with it. But understand, mass and weight, not the same thing. Not the same thing at all. Force. Force is a very broad definition. It's so broad, sometimes when you get a definition, You think like, oh, we figured out what this thing is. That's true sometimes. And sometimes the definition is, we're going to make this thing so freaking broad that even if we discover something later, it just falls into the category. Mass is kind of that way. Anything that takes up space is anything. So if we find anything later, then it gets its mass by definition. Force is any interaction that tends to change the motion of an object. So right now, we understand in science that there are 4 fundamental forces. But if in a week's time a scientist does some sort of study and finds another thing that affects things, they can go, well, I guess that falls into the force category because it's anything that tends to change the motion of an object. Intuitively, it can be seen as a push or a pull. Somebody comes along a little bit later today, gives you a shove, that's a force. As you sit here right now, what's pushing on you? Okay, which way?
Yeah.
Is that the only thing pushing on you?
No.
What else is pushing on you?
The shine.
This is why you need bullying. This is why you need bullying. And everybody laughed at you, and I don't know if it was a joke or if it was serious, it kind of felt serious. Anyway, point. No, what else is pushing on you? Good night, people. What? Feel it. Like, use your nerves. No. Well, yes, actually, technically, we're not getting into that one right now. You're not wrong. You're not wrong. I'm sorry. I have angst, high angst there, which you were accurate for. No, what's pushing on you?
Yourself.
No, you can't.
Ground.
Your seat. Which way is your seat pushing you right now, guys?
Up.
Up. Because if it wasn't there, gravity would force you to fall until you hit the ground. And which way would the ground push you? All right, we'll get to that later. Force is measured in newtons. We'll talk about that later on. There's 4 fundamental forces. We've already discussed one today. There's one that is very common and very popular. What's it called? Gravity is a fundamental force, although we are going to discuss it in a greater depth than many of you have probably thought about it prior. So what is gravity? Gravity is the attraction between any 2 masses. Any 2 masses. You got mass? Remind me again what mass is.
Number of atoms.
Number of atoms.
Okay. Do you have mass?
Yeah.
Yeah. You're anything, right? Do you have the same amount of mass that you did when you were a baby?
No.
If your mother say, I sure hope not. Okay. How big was your baby? 120 pounds. No, they weren't, because you would be dead. All right. So, where'd you get your mass from? Where'd you get it from? You were a baby. You're not. Where'd you get your mass from? Food, correct. We eat on the regular, that builds us up bigger and bigger and bigger, okay? As a matter of fact, your mass changes a lot more throughout the day than you probably think about, okay? Don't believe me, I'm using weight right now synonymously. I'm not supposed to see previous conversation, but weigh yourself before and after lunch, or weigh yourself before and after using the restroom if you want to be gross. But yeah, your mass changes throughout the day. You have more atoms, you have less atoms. It oscillates a lot more than most people's standard think, okay? Now, you have mass, as we have previously discussed. Do all of you have the same amount of mass? No. No, why not? So all of you are made of a different number of atoms, and thus you have a different mass. Cool? All right. Does this chair have mass?
Yeah.
Okay. So let's get serious for a second, guys. I think it's important we have this conversation now. You attracted to the chair? You attracted? Sorry, homophones, my apologies. Attraction, different scientifically, not romantic styles. But yes, are you attracted to the chair?
Yes.
So do you have gravity?
Yes.
Why is that so weird?
It's not strong.
It's not strong. It's definitely not strong. It's not a strong attraction between you and the chair. I mean, obviously you're attracted to it. I can see it on your face. But like, it's not a strong attraction to the chair. So let's discuss that. Okay, there's a second, a third, and a fourth one. Write those down. The placeholders for later. We'll get to those sooner than we get to the other 2. But let's talk about gravity for a hot second. Gravity depends on both objects' mass. Both objects control how much gravity there is between the 2 of them. Gravity depends on mass, as we already said, but it also depends on the distance between those 2 objects. And finally, and I'm going to talk about all these a little bit more in depth, so listen up here. This is the true answer to why you don't have an attraction that's noticeable in the chair. Gravity is stupid, stupid weak for a force. In order to have any sort of significant effect, it requires an incredibly large amount of mass and it to be pretty darn close. Now, understand I right over here write astronomically speaking. Because let's talk about the most common force of gravity that you're used to. When we say gravity, most people think this. The ball falls to the earth. They don't usually think about it with two objects. What are the two objects here?
Ball, earth.
The ball and the earth. That's right. Okay. Now this ball and where'd she go? Do you need her back?
Her back.
Okay, done.
Go, bro.
All right. This ball, one I saw previously, and this ball have a different pull to the ground. Yes? Okay? For those of you on the video, I'm holding up the giant tennis ball and the bowling ball named Sally. All right. So, she's got her name printed on her forehead. It's right here. Sally. All right. Anyway, Sally's been in this department longer than I have. Anyway, so why is Sally got more of a pull on the ground than the tennis ball?
More math.
Ah, there it is. More mass. Heavier, blah, blah, blah. We'll get to that later. Okay. Now, what are the two objects in question? You said it already. Let's say it again.
Earth and the ball.
The earth and the ball. Right. Those are the two objects. So you guys have changed mass throughout your life. Yes? Has your force of gravity changed? Yes. Because?
Got more math.
Because you got more mass. All of you in here do not share the same force of gravity. Why do all of you have different force of gravity? We talked about this earlier. We all don't have the same masses, and therefore we don't have the same force of gravity. So let's talk about this in a little bit more interesting perspective. Let's say tomorrow an asteroid comes by and blows off half Earth, and we survive. Okay, let's not worry about that right now. Apparently, what would that mean to your force of gravity tomorrow?
It would decrease.
Correct. You would not have the same force of gravity tomorrow because
The earth would have
the second object now has less mass. Why is there no force of gravity in space?
There's no object.
There's no second object. Literally no second object whatsoever. Now let's talk about this. Firstly, the astronomically speaking part. I might say, how close is the Earth? And you might kind of like correctly there was I'm touching the Earth, so like 0. Except no, if you zoom out, when we say how close things are, we're looking center to center. So are we actually at a 0 distance to the Earth? No, it's actually 4,200 miles is roughly the radius. I'm rounding for the sake of simplicity of numbers, but is about the radius of Earth. So we are 4,200 miles away. Now, is that close? Yes and no. For us, it's obviously no. 4,200 miles is a very long distance, but astronomically speaking, is that stupid close?
Yes.
Yeah, it's pretty stupid close. Okay, let's talk about objects that are big enough to us and close enough to us that we see their effect in our solar system. Mass does not weight, blah, blah, blah. Okay, major effects of gravity that we see. What objects are big enough and close enough to us that we see an impact? Let's start with the easiest one.
Sun.
The easiest one.
Oh. Moon.
The easiest one. Why does this say this every year? Yes, we just got done talking about it. The Earth. Okay, the Earth is big enough to us and close enough to us that what effect do you see? G, 9.8 meters per second squared. Now this is an excellent time to discuss this. When I use the word gravity, it's a little bit synonymous. It's a little bit kind of vague. So there's two major things that I'm going to use now to distinguish. We have actually previously been talking about G. This is known as the acceleration of gravity, or kind of the effect of gravity that we see. And we always see it at 9.8, which is why we kind of left it alone. It's an acceleration, blah, blah, blah. Okay? But this is the force of gravity. This is causing that particular effect. All right. You nailed the other two. Somebody give me another one. The moon. What effect do we see? Tides. Okay. Next, the third one. What effect do we see? What effect do we see because of the sun? What's that? What did you say? Yeah, we go in a circle. Because if the sun wasn't there, we would go in a straight line. Of course, if the sun wasn't there, we would be dead a long time ago, blah, blah, blah. Wouldn't exist to begin with, ha, ha. But anyway, yeah, because we go in a circle, the sun. Big enough and close enough. So this is a little bit tricky because if you know any sort of astronomy, you might disagree with me on this, but take it for what it is, and we can talk later about why this is sort of wrong. We don't see the effect of Jupiter. Why don't we see the effect of Jupiter listed up here?
Really far.
Yes, there it is. It's far away. Is it bigger than the moon?
Yes.
Much. Yes, it's much bigger than the Earth. So why can it be so much bigger and not show an impact? Because distance is also a thing that affects this. We often don't think about distance, but it is another piece. In other words, if you left Earth, like if you were a superhero and took off, okay, would gravity of Earth affect you forever? No, it would slowly fade out, get weaker and weaker and weaker and weaker, until eventually we would round down to zero. Now, technically, it does affect you everywhere in the universe. There's a whole conversation about that, about how fast gravity actually travels, and blah, blah, blah. We can get to that in physics, too. All right, moving on. So, what is weight, then? We know it's not mass. What is it? It's actually the word I've just been using. Weight is the common name for force of gravity. So if you want to be a little bit more scientific, rather than when somebody, you don't want to ask somebody what their weight, because that's embarrassing, you ask them what their force of gravity is. It's literally the same thing, but it sounds a little bit nicer. So let's talk about force of gravity, weight, and mass. For starters, I already mentioned the difference between acceleration of gravity and force of gravity. What's the difference between force of gravity and weight? There is none. They're the same thing, literally the same thing. So if I ask you what your weight is, I'm asking you what your force of gravity is, and the rules that we have just discussed that affect force of gravity are what we're talking about, right? So I should be able to say, what two objects affect your weight?
That's just
No. What two objects in question? Because remember how many? The Earth and you. You are the two objects in question. What's the other thing? Your distance between you and, of course, the center of the Earth. So let's take an astronaut, okay? And that astronaut's on Earth and has a mass of 100 kilograms. Its weight is 980 newtons. Now, you're not familiar yet, probably, many of you, with newtons. So I'm going to use the synonymous of weight and say pounds, okay? Newtons and pounds both measure force. They can both be used. So somebody with a mass of 100 kilograms also has a weight of 220 pounds. So we take this astronaut and we teleport them to the moon, or fly them, I don't know, whichever. Okay? Does their mass change? No. How come?
Because they're still the same person.
Not quite what I'm looking for. I think you're there, but I need to say
Same number of
the same number of atoms. Mass has not changed. They have the same number of atoms. Correct. Is their force of gravity / weight different? Yes. Careful on this answer, because if you understand what's going on, you should answer one way, and if you don't, you're going to answer the other. Why?
distance. Because the second
Force of gravity is
object
less.
changed.
The second object changed. And that's what people usually say. They go, gravity's less. Why? Why is gravity less? Gravity is less not by magic or because it's real simple. Why is the gravity of Moon less than that of Earth's?
It's smaller, it has less
That's it.
atoms.
Pretty much it. I mean, there's one other thing involved. We'll talk about that in a second. But here's easy stuff, guys. The biggest joke, by the way, in all of sci-fi is that every single planet everybody goes to always has the exact same gravity. What would have to be the case in order for that to occur?
They're all the same size.
They'd all be the same size and the same mass. Is that very likely? Well, let's put this in perspective. There are currently 8 planets in our solar system, and none of them have the same size and mass. You've probably heard this before. Which planet's gravity is closest synonymously to Earth's? Do you know how close it actually is when it's close?
No.
It's 30%. It's 30% of the gravity here. So here's an easy thing. Get out your calculator, punch in your weight, or whatever weight you want to pretend to be, and multiply by 0.3. That's how much you weigh on Mars. How much you weigh? Well, somebody who doesn't care, tell me how much they weigh.
54.
Well, how much do you weigh right now, if you don't mind my saying? 180, okay? So 180, you weigh 54. Do you look any different on Mars? No, You're the exact same person. You just literally weigh less. So, what would naturally happen to your muscles then over time?
Degenerate.
Yeah, to lift a 54-pound person rather than a 180-pound person. Our muscles don't have any magic to them. Why do we degenerate? It's not because of the weird sciencey whatever. It's just my legs weightlift every single day. What do they weightlift? They weightlift my weight, which is why larger people tend to have stronger muscles than less big people. That's how it works. Okay? If you become automatically a less big person, your muscles get weaker. Hilarious video, by the way. Totally look this up sometime. Astronauts falling over on Mars. Astronauts are some of the best humans. They're like the smartest. They are the most athletic, and they're also like the best, social person. Like you can talk to an astronaut, and they're like ridiculously good at just like this type of conversation or whatever. So amazing, and to watch them fall over all the time on Mars was just incredible. The reason why they fall over is their legs are built for Earth. So if they regularly carry around about 200 pounds and they go to the moon has 1/6 the gravity that Earth does. So you take that 200-pound person, or actually let's just do this, 220-pound person on Earth, divide by 6, they now weigh 37 pounds on the moon. It's not, they fall over a lot. One more thing about the moon conversation real quick. Let's see if you can figure this one out, okay? I said that the moon has 1/6 the gravity of that of Earth, and that is true. But the amount of mass it actually has is about 1/100th that of Earth. So what is the issue there? Discuss quickly in your group. Why is it as big as it is? If the mass is like 100th of Earth's, why is its gravity that big? Discuss quickly. We'll be right back after these messages. All right, I heard a bunch of people say it, so we'll just go on. What's the answer? The distance. Yes, the distance between the objects. Like if I talk about the distance between you and this chair, you have a much better distance right here between you and the chair than the Earth does on you. So why don't I affect the chair? Well, gravity's super weak, and I don't have that much mass. Let's put in perspective real quick how much mass we're talking real quick. Did I still lose the marker? How? It wasn't even different. All right, here we go. All right, real quick. In here, if you are about 50, if you're about 100 pounds, you're about 45 kilograms, okay? If you're around 150 pounds, you're about 70 kilograms, and about a 100 kilogram person is about 220 pounds, as we've already discussed, okay? You can obviously kind of fit yourself somewhere in that particular one. Meaning that for the most part, everybody in here is around times 10 to the first in scientific notation, yes? Maybe the second if you're a little bit bigger. Here is the mass of Earth. I'm going to write it out without scientific notation so you can feel it. The mass of Earth. 5.98 times 10 to the 24th, or 598 and 22 zeros. That's the mass of the Earth. That's how much we're going to change it over there. That's how much mass you need to pull this off. It's a bit. It's a bit. Okay? I one time had somebody always ask the infamous question, what if everybody on the planet got into one particular spot and jumped? Would we affect things? Well, let's talk about that for a half a second. There's roughly 8 billion people on the planet. Let's just go ahead and assume, for sake of simplicity of math, that everybody's 220 pounds. My baby son would disagree with that average, but let's just go ahead and stick with 100 kilograms for sake of simplicity of math. 8 billion would multiply by 100, which would put us at 800 billion kilograms of mass of human beings. Well, that's a big number until you realize it affects that spot right there by 8. If all the human beings on Earth got in one spot and jumped up and down, do you think we'd affect Earth? Let's put it in this perspective. Here's the rough equivalent. If I took a fly and I took a scalpel and I could take 1,000th off of that fly, and then I could take like a super small tiny laser scalpel and take 1,000th off of that 1,000th and then flick it at you, it'd have about the same effect. All right, very big. Moving on. All right, we talked a lot. Oh, darn it. That was a mistake. Where were we? Right here. Okay. Show current slide. Here we go. Quick. All right, so Mass is a physical quantity. It's stuff. You can count it. You could technically count the number of atoms. That's what it is. Weight, or force of gravity, is the effect of that mass. If you teleport you to any sort of planet or star in the solar system, your mass isn't going to change. Conservation of mass, well, technically if you go to a star, it sort of changes depending on how we define you, because you're going to vaporize into like all of your individual atoms. I mean, your atoms will be there, but like you as you probably won't be a thing. It's not important. Point is, your atoms will stay the same. Your weight, or your force of gravity, is different because you're compared to a different number of atoms. So, mass is not weight. They're not the same thing. Mass is the stuff. Weight is the effect. As I said at the beginning, here we go. The effects of mass. There are two properties of mass. I told you this at the beginning. I skipped over that because this is all right here. What's the first property of mass? All mass has gravity. Or, I'll ask you this question throughout the year. What are the two properties of mass? And for this one, you say, all mass attracts all other mass. That's gravity. So while you're writing this down, I will tell you the world's lamest scientific pickup line. Okay? You go up to the person you're interested in, and you look at them, you look them dead in the eye, very seriously, and you say, you're attracted to me. And technically it's true, although it's a little bit a homophone, but there's two responses that you can use, by the way, if you're not a fan of these particular advances. The first, and easiest by far, is you look at them and you go, nerd, and you walk away, okay? That's the first thing that you can do if you're not a fan, okay? The second thing that you can do is you can respond scientifically. Then you go, yeah, but basically it's so insignificant that we're just gonna go ahead and round down to 0, all right? Because, yeah, the amount of attraction between you is basically 0, scientifically speaking. Yes, it's there, but it's like times 10 to the -7th or something like that. It's nothing. All right. And then there's a second property. Like I said, I'll talk about that later this week. Let's move on. It took forever. Oh, I'll talk about this very, very quickly. I always put this up here. I never have enough time. This is on the slideshow. There's a really cool thing on Wolfram Alpha that you can actually calculate G at different spots on the planet. Like you can type in what is G in Alton, Illinois, and it will calculate it currently with models and understanding kind of like what's happening underneath the surface of the planet. For the most part in Alton, we're very close to 9.80, which is why I use 9.8 here. If you get down to sea level at a lot of different spots, it's actually 9.81. But if you go over to actual like Denver, Mile High, specifically over in the Rockies, you can get as low as about 9.78. Why does it get lower when you get up there? Distance, further away, that's it. That's all it is. All right. 4 fundamental forces. Second one, electromagnetism. The great thing about electromagnetism is that it sounds complicated, and it really isn't. You've been in 8th grade. What do positives do to each other? What do 2 positives do? They repel, yeah, or push, that's fine. What do 2 negatives do? Do not say cancel. So how many of you say cancel? Scientifically, yeah, they push. They also repel. What do opposites do? There it is. You just discussed electromagnetism in a nutshell. Now, if we take those basic rules and our understanding of what the atom looks like, see Bell-Raymond, then we should be able to discuss kind of a little bit more interesting stuff here. There's a third and a fourth one, by the way. These will go much quicker, I promise. But before we get too far, you've already written this down. Don't write it down again. Or you can. I can't stop you. But there's the carbon atom over there. Actually, no, it's not carbon. What is that? Is that beryllium? Yeah, it's beryllium. All right, anyway, point is, if you think logically about this, yeah.
Is electromagnetism a property of mass or a force?
Yes.
Which one?
Oh, no, it's a force.
Okay.
It is a force. Okay. Sorry. It is a sort of a property. It's not important, but no, it doesn't fall in the property of mass. It's one of the 4 fundamental forces. Okay, so all we said is negatives repel, positives repel, opposites attract. That's it. Based on those rules, there are 2 stupid things about the way the atom looks. If you think about this critically, as opposed to just like somebody told me this is what it looks like, and so I suppose it's what it looks like. Have you seen an atom? Do you know? Okay, but if you think about it critically. Why does this look dumb? Yes, Brianna.
The negatives are going.
Yeah, for starters, the negatives aren't being pulled into the positives. Okay? Now, there's theories on that. We can get into those a little bit later. Of course, you can go with Bohr's sort of model and start to think of them as planets rotating around, which is sort of the same reason why we as a planet don't fall into the sun, because we have a circle, and there's a whole thing to that, chapter 7. But then, yeah, why is that not the case? That gets a little bit more complicated when you talk about physics 2 and upper level chemistry. You can talk about Heisenberg's uncertainty principle, blah, blah, blah. Let's not do that right now. The other one is what I wanted. What's the other weird thing about this? What are the positives doing in the freaking middle? What should they be doing to each other? So why are the nuclei not permanently exploding? The answer to that question, by the way, has to do with the neutron. Neutrons do nothing electromagnetically speaking. Meaning, what does a positive and a neutral do? Nothing. What does a negative and a neutral do? Nothing. Okay? It's the other two that matter. The neutrals are in there for something that we'll discuss here in just a minute. They hold things together, blah, blah, blah. We'll get to that later. All right. So, we talked about this already. Let's talk about effects. Let's talk about interesting things. For starters, am I made out of mass? So are you, yes? And what's on the outside of all of those atoms? Electrons. Very good. Is this chair made out of mass?
Yeah.
What's on the outside of it?
Electron.
And what do electrons do to other electrons? Yep. Most of the pushes that you are used to in real life are just this. What do negatives do to negatives? They repel. You can't see the negatives, and so you don't think about it that way. Okay? Why is the chair currently pushing your butt up? There's negatives on the outside of the chair. There's negatives on the outside of your butt. They repel each other. That's it. Okay? If you could actually, according to this, by the way, you technically don't ever touch anything. Because if you look very, very closely, there'd be negatives on the outside of this, and what does the force between these negatives do as it gets closer? It gets bigger. It's bigger. Bigger. It's not going to go infinite. Eventually, it's just going to settle there. As a matter of fact, if you could look underneath my shoes very, 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 very close, what you'd find is I'm hovering. Not impressively. Okay? Aha! Wait. Like, I'm not going to walk into a class where we haven't had this conversation already. Like, look at me. They'll be like, you're standing there. You look like an idiot. What are you trying to show right now? Like, I'm hovering. Yeah, great job. Anyway, yeah, it doesn't technically work like that. Ooh, let's do my tape example. You can do this yourself. Take a piece of tape. By the way, the tape example, if you've ever done laundry, especially during the winter, you do this example all the time. But all I'm going to do is put a small tab on a piece of tape. I'm going to do it again. And I'm going to put the sticky side of the tape on top of the smooth side. It has to be different surfaces. And I'm going to go ahead and guess that you can answer this next question correctly, even though you don't have the background for it. Yes, I know. Go give them their tests. I haven't forgotten. All right. Which side holds on better to electrons, sticky or smooth?
Sticky.
That's why it's sticky. That's literally why it's sticky. Put something sticky on you, it's just holding onto your electrons better. So, but yeah, point it. So if they got into a tug of war, the sticky and the smooth side, who would win? Sticky would win. And so more electrons should be on the sticky side, right? Those electrons came from somewhere. Where they come from? Smooth side. So the sticky side becomes what charge?
Negative.
Negative. What does the smooth side become?
Positive.
And what do negatives and positives do?
Attract.
Yes, they do. Wee. Now, I said, if you have been doing laundry, specifically if you ever do it without dryer sheets, then you've done the exact same thing. You take two different materials, one holds on better to electrons, and you pull them apart, and they're attracted to each other. Why? Because one stole electrons from the other. And you know that to be the case, because as you're doing it, there are these tiny little shocks. You know what those are? Those are electrons jumping through the air over to the positive side. That's why they're there. Or I could take two pieces of tape and set them on the same material. In this case, the table. Which one holds on better, the table or the sticky? I don't care. It doesn't actually matter, but I think it's the sticky. I think both of them end as negative. So both of them end as negative. What do two negatives do to each other? Better. Would you stop holding them? I know, polarization. I get it. It's cold outside and you're doing polarization. And you're not showing very well here. Yes, I know. Darn it, I waited too long. There it is. Here we go. They repel. All right. Next, Spainhour running into the wall. Spainhour runs into the wall. Why doesn't he go through? Electrons. Electrons on the outside of the wall. Electrons on the outside of my face. I don't have a large enough mass to crash through there. See a conversation about Newton that we can get into a little bit later. But these are the common names of electromagnetism that you're more used to. These are the ones that we will use. Why? Because there's electromagnetism all over the freaking place. If you think about it today, your pen is making a right now on that page because of electromagnetism. Because there's positives in that paper that are holding on to the negatives in that lead, and that lead is being held onto the page, and those positives and negatives hold together, holding that mark on your particular page. As you walk from place to place, you don't go to the forward, there's negatives and negatives. But why can you push at all? Well, that gets us to the first one. Friction. Friction is a common name for electromagnetism. So what I want you to be able to do with these is I want you to understand why they're electromagnetism and also sort of just how they work. Let's talk about air friction. You can write this down, but just pay attention more. Okay, watch. Is there mass in air?
Yes.
And what is on the outside of air?
Electron.
And electrons on my face. So I walk this way. Which way does air push me?
That way.
That way. Just going out this way. And if I go this way?
The other way.
The other way.
That
What if I'm free falling? What if I jump in a skydive? Pushes up, right? Or if I jump up into the air, it technically pushes down because it's just pushing the opposite way. That's it. Water, same thing. Literally the same thing. Why does water affect you more than air?
Because
There's more to this. There's more to this. That's it. Okay, surface friction's a little bit different. Take your hand, run it along the table. There's a pull backwards. Basically, when you think of this one, I'm trying to get quickly through this so that I can finish this in about 10 minutes. Okay? Think of it like, okay, here's surface A, okay, made of positives and negatives. Here's surface B. What are those negatives doing to each other? What are the negatives doing to each other? Repelling. So this is your hand, and this is the table. That's why your hand does not go through the table. The electrons are pushing. But what are these positives doing to the negative, and these negatives doing to the positives? Attracting. That's what we call surface friction. I've already done an example of surface friction for you with the tape. That is literally why the tape example worked. There was positives that held better onto negatives, and so it ended up as negative, blah, blah, blah. But let's give this guy a name over here. This is something you probably are less familiar with. This is known as force normal. Now, force normal is a little bit tricky because you could technically put it in a lot of different spots. So we're going to get a little bit specific here. We're going to use force normal when it's a solid, immovable object that's pushing against you. All right, let's get you guys' tests. I'm going to finish this up here in a couple minutes. Actually, hold on, let me stop that first.
A boulder.